Alright, in this video, we study the geometric meaning of numeric vectors, especially real vectors. So let's start. We mainly consider two-dimensional vectors so that we can draw pictures on the plane. Okay, so suppose we have a vector and let's say vector v that is made of a and b, and a and b are real numbers. Okay, and that vector may be represented as an arrow on the plane. And what's important is that if we make a coordinate system in this plane, let's say x coordinate and y coordinate, and we don't care the position of the vector. So this vector is the same vector where if it's here, or if it's here, or if it's here, or if it's here, wherever. We still consider all these vectors the same vector as long as their length is the same and their direction is the same. Direction may be, for example, quantified by the angle from the horizontal axis, right? So this angle and this length, if that's the same, as long as this is okay, that's the case, then all the vectors are considered to be the same. Let's call this source point as S, and this the end of this arrow, call it T, so target and source. So we have some, in two-dimensional space, we have 2 points, the source and the target. So let's say the coordinate of this source is xs and ys. And the coordinate of this target is xt and yt. So in that case, if you project the target point on this horizontal line, then this length is equal to a. So this a, okay? And if you project this target point onto this vertical line that passes through the source point, then this length is b, okay? In this particular picture, a and b are positive. If a is negative, then the arrow should look this way. So the projection onto the horizontal line becomes negative. So if we project this vector onto this line, then the result is this arrow, and that will be a, and that will be a negative number. So in the case of negative a, this projection points to the left, or it's positive. If it's a is positive, then this projected arrow will point to the right. And similar for b, the second component. If b is positive, then it is the projection onto the vertical line points to up. And if it's negative, it will be like it will look like this or this. And if we project onto the vertical line, it becomes points to down, points down like this. So b is negative and a is negative, and a is positive and b is positive in this case. Okay. So as such, if we have a vector v that is made of a and b, then so although this arrow can be anywhere in the space, we can just translate to this point, so that the source point of the vector matches the origin. In that case, the x-coordinate of this target point becomes a, and the y-coordinate of this target point becomes b. So that's what this vector is. Now, if we have another vector, say w, made of c and d, and of course c and d are real, then it may be something like this, right? Maybe let's change it a little bit, like this, let's say. So this is V and this is W. So if we add these two, we get V plus W, that is, so A plus C and B plus D. So this addition can be represented as a vector. So first we have V and move this W so that its source point matches the target point of V, and then connect the origin to the target of W. So this resulting arrow becomes the sum of two vectors. So this is V plus W. As you can see, it has first component is A plus C and the second component is B plus D. Since if you project this W onto the horizontal axis, this length is C and this length is D. So this, the sum of the two vectors have the x-coordinate of A plus C, right? Because we have A and we have C here. So if we add them, we have A plus C. And same for the y-coordinate, that is this. So first we have B from V, and then we have D from W. So if we add them, we have B plus D. So this point, the coordinate is this. Next, consider scalar multiplication. Okay. So suppose we have this vector, V, and that is A, that has components A and B. So V is A and B, and if we multiply by C, let's say lambda, and lambda is a vector, then the result is lambda A and lambda B. So if lambda is a positive number and that is greater than 1, then the resulting vector becomes something like this. Because the direction doesn't change. Both x-coordinate and y-coordinate are multiplied by the same number, lambda. So this proportion, so A to B doesn't change. And so if the proportion is A to B and lambda A to lambda B, so lambda B over lambda A is equal to B over A. So this proportion doesn't change. That means this angle stays the same between this and this transformation. So what we have is a vector that directs to the same direction but of different length. So that is scaled by lambda. Okay, so this length and this length have the ratio of 1 to lambda. So 1 to lambda. And that you can check by directly calculating the length of this vector and this vector on this plane. Okay, on this plane, the length of this is by using the Pythagorean theorem. So this length is A and this length is B. So the length of the vector V, which we usually denote by this, is the distance between the origin and the target. So that is square root of A squared plus B squared, right? And the length of lambda V, which we usually denote as this, should be, because the coordinate of this is lambda A and lambda B. So that's square root of lambda A squared and lambda B squared. And we have the same factor lambda, and so we can take it out, but it becomes absolute value. In general, lambda can be negative, so let's take absolute value here, and A squared and B squared. Okay, So the ratio between this and this is lambda. Uh, to be precise, it's lambda absolute value. And of course, when lambda is negative, then the direction becomes opposite, okay? But the angle doesn't change, so the same angle, but, well, same angle, but just opposite direction, so 180 degrees opposite. Okay, and when lambda is less than 1, then and positive, then the length of the vector shrinks instead of extended, but it becomes shorter. So if you think you understood enough about the geometric meaning of vector addition and scalar multiplication, then you can skip the rest of this video and go to the next one. In the following, I will explain what we exactly mean by regarding two arrows the same vector if they have the same length and the same direction. And for that, we introduce equivalence relation between arrows. So as we explained before, in order to specify an arrow in a space, we need to specify 2 points, that is the source point and the target point. So let's say the source has the coordinate xs and ys, and the target has the coordinate of xt and yt. So in that sense, an arrow is made of 2 points, and that each of which is made of 2 real numbers. So to specify an arrow, we need to specify 2 points, xs, ys, and xt and yt. So this pair of 2 points specifies an arrow in space. Okay, so this is an element of R2 times R2. So this belongs to this and this belongs to this, and which is similar to the 4-dimensional space, right? Because we have 2 real numbers here and 2 real numbers here. So in total, we have 4 real numbers here. So let's say this is an arrow called A, okay? And let's consider another arrow, B. Let's say source point is U, so XU and YU, and the target point is, let's say, XV and YV. Okay, so let's, for example, this is A, and this is B. Okay. Now we introduce an equivalence relation between these two arrows in the following manner. So that is, A and B are defined to be equivalent if xt minus xs, so the difference between this and this, is equal to the difference between this and this, xv minus xu, and not only this, but difference between this, the y coordinates. Okay, so yt minus ys is equal to yv minus yu. So if these two conditions hold, we consider these two arrows to be equivalent. And we will show that this is indeed an equivalence relation. So let's show that. Remember the definition of an equivalence relation? First, we need to check 3 conditions. Okay. First is reflexivity. Reflexivity. So that is for any arrow A, we need to show that A is equivalent to A itself, right? So we need to show this. But that is trivial, right? Because if we have 2 arrows, A and A, then if A, let's see, if A is this, if A is this, then xt minus xs is equal to, of course, xt minus xs. And yt minus ys is, of course, equal to yt minus ys. So therefore, by definition of this relation, A is equivalent to A. And 2, it's symmetry. Second, we need to show this. And symmetry is we need to show if A is equivalent to B, then B is equivalent to A. So let's say we have this A and this B. Okay, so suppose A is equivalent to B, then by definition we have xt minus xs is equal to xv minus xu, and yt minus ys is equal to yv minus yu. But of course, this equality is the equality between two real numbers. So this is a real number and this is a real number. So of course, it is symmetric. Therefore, xv minus xu is equal to xt minus xs, and yv minus yu is equal to yt minus ys. So this means B is equivalent to A. So the symmetry is symmetry holds. And the third condition is transitivity. So this relation, it should be transitive, right? So that means if we have three arrows, and if A is equivalent to B and B is equivalent to C, then we need to show A is equivalent to C, right? So let's show this. So suppose in addition to this A and this B, let's say we have another arrow C that is defined as, let's say, what should I write? Okay, xp and yp and xq and yq. So let's say another point is this. Then suppose these two conditions, okay? Suppose A is equivalent to B and B is equivalent to C. Then, according to the definition, this means xt minus xs is equal to xv minus xu from here, and same for y, v minus yu. So this comes from this, and same thing for this, that is xv minus xu is equal to xq minus xp. So xq minus xp. And same for y, yq minus yp. Okay, now from these two, we need to show this. So x t minus xs is equal to this, xv minus xu, but this one is equal to this, but this one is equal to this. So this is equal to this, and similarly we can show that yt minus ys is equal to yq minus yp. So therefore A is equivalent to C. Therefore this is indeed an equivalence relation. And we are done. So because of this equivalence relation, any arrow, let's say something like xs and ys and xt and yt is in particular is equivalent to this point 0 0. The source is the origin, and x prime and y prime, where this x prime is equal to the difference between xt and xs, and y prime is equal to yt minus ys. So we can always transform or translate any arrow to this type of arrow where the source is the origin. Okay, so in this way, we can define an equivalence class. So equivalence class of an arrow. So we can define equivalence class of an arrow that is represented by this arrow. So 0 0 and x prime and y prime. Equivalence arrow is the set of all arrows that are equivalent to this arrow. Okay, equivalence class. So since the source is always origin for this representative, so we all need the coordinate of the target point. Okay, so instead of writing like this, we write like just using the target point, we write like this and call it a vector. Okay. So a vector is an equivalence class of arrows. And this equivalence class, of course, belongs to this quotient space. So to begin with, we had this space, but now we consider equivalence class by this relation. So this equivalence class belongs to this, and this is actually represented by this, which only needs two real numbers. So this is actually similar. Let's write like similar to two-dimensional space. Okay, and this two-dimensional space is the vector space. And so far we have been only considering two-dimensional space, but vector space, but the same argument applies to any dimensions. So for n-dimensional space, we can define an arrow by 2 points in that n-dimensional space. So in case of n dimensions, we have to specify n real numbers for the source. So x1, x2, and so on, and xn. And y1, y2, maybe x and y are confusing, so let's use other symbols. Let's say source 1, 2, and Sn, n-dimensional space, and target t1, t2, and so on, and tn. So another point. So this is an element of this space. So this belongs to this, and this belongs to this, and their pair belongs to this. And we can define the equivalence relation similarly by considering the difference between T1 and S1, T2 and S2, and so on. So the vector, so n-dimensional vector space, so vector space is defined as the quotient space of arrows by this equivalence relation. Okay, so that's all for this video, and see you later.